Okay, we start up. Any questions before we begin? Okie doke. So today I want to go through a little bit material. You have received some files already. I put out some new ones for you. So let's start by looking at open form material. And you had something called tips and tricks. There were some points here I wanted to show you. We have looked at this one before, so you don't have to go through everything here. But it should be somewhere. Where are we? Where are we? Mesh quality. Here, setup for the different schemes. Nice to know. Very robust, but too diffusive. Okay, and then more accurate and also stable. And then even more accurate, but might be a little bit oscillatory. And same goes for these other schemes, and maybe not so important, but still. But it should be here somewhere that we have, when you have non-orthogonal meshes, how to choose a scheme. So now when we start messing around with the different meshes, distorted meshes, yes, you will have non-orthogonality. Then you have to use check mesh and see what he reports. And as it says here, if that one is more than 85, forget it. Make it a better mesh. So that's one rule. But if you are going to use, say, a highly non-orthogonal mesh, then here you have sort of a setup that might improve your solution. So these pages here could be something for you to use now in this exercise to make a good and stable solution, more accurate. We have the analytical solution, so yeah, have a look at these setups with the non-orthogonalities. And also, how many of these correctors, non-orthogonal correctors, should you use? Well, depending on what check mesh reports. It might be actually a good idea to use this as a one, even when you have pure rectangular cells. It might even improve your solution, meaning he does one more iteration per time step, but it could be a good idea actually, as it says here, to do at least one non-orthogonal correction. Under relaxation factors, normally you won't mess around with these unless you have something that explodes all the time. And if you use a pure simple, definitely you're going to need them. But nobody's using simple. Everybody's using simple C. And to switch between them, you had the word consistent, yes, no, in the setup. And when it's simple C, much more robust. And then should speed up the calculation process. Yeah, he goes through a little bit here with the different solvers as well. Might also be a good idea to have a look at these setups. So you can start with a sort of a bigger tolerance, and then you can improve it after a while. Yeah, I won't go through this one so much in detail. So several options. Okay. Then I want to have a look at this file, post-processing. Here you might find some snacks. And yes, this is something we are going to use more and more. And using these functions you sort of include in the control dict file, that can be quite nice actually. And also have a look at this post-process, how we can extract data, how we can calculate this and that and do a lot of things. So let's just have a look. So here, for instance, you have a whole bunch of these function objects that you can include into the into the control dict. And well, the Qur'an number, normally not a problem. We will have that one displayed anyhow when you're doing a transient simulation. Finding field averages, field values, okay, maybe not so so nice. Vorticity, that's something we are going to look at today. Y plus, always nice to know. So you can automatically get the Y plus while simulating. And also these two, something we are going to look at. Find the force on an object inside your domain. You are simulating the flow around the car. What's the drag force on the car? Either as a force in Newton or as force coefficient, non-dimensionalized. Wall shear stress, that could be nice to know if you're doing a turbulent simulation. Absolutely. And yeah, that should be sort of the most important ones. And how such a function looks like. So you write it at the end of your control dict file. So you sort of have a standard setup here. Name, what object type, what library to use, and then true false. You can switch it off if you want. The log, yeah, you want to have some answers, so he displays it on the screen while he simulates. If that one is off, it's false, then he will still calculate it, but he won't display it on the screen, but you'll find it in files afterwards. He creates a folder called postProcess, I think. So you find everything there. How often do you want him to execute this? So that should be sort of standard. And yeah, and then it's specific how this, well, depending on the function, of course. So we have some examples here. And you have a whole bunch of these. You can actually look at the source code if you want, but normally we don't mess around with that. So to use them, find a tutorial that has an example for it, and then copy it from there. Much easier. So here you have sort of the standard setup inside your, say at the bottom of your control dict functions, and then you can have a whole bunch of these. Absolutely. Let's see what they have here. Here we have a nice one. It's a type forces. And then, yeah, we write it at every single time step. Why not? Enabled, meaning yes, it's operative. And then what patches to look at? I mean, he will report forces in Newton on the different walls that you have. If you have several different type of walls, then he can display actually the forces acting on these different walls. If you had more than one object, for instance, or you want to have a look at the force as part of an object, you just specify the different walls here, the different patches. The fields, yes, he's going to need pressure and velocity to calculate the force. But that's all he needs. And for incompressible flows, yes, you have to give him a reference density. For a compressible flow, then of course you need the field rho here as well. Then he's going to need the density also. But for incompressible, you just need a reference. Central rotation, well, this force function, he can also give you the torque acting on an object, not only the forces in x, y, and z direction. And yeah, so there you have a little bit more detail, the same file. And if you go to the force coefficient, this is something we are going to use. The force coefficients, that's just the non-dimensional forces. You will have lift and drag. Drag in the, well, you specify the direction and the lift, typically then in the cross-stream direction. And it's more or less the same setup. But we have something in addition here. Central rotation, again, normally we are not so interested in the torque. We may be, but normally not. But we are going to need the direction for the lift and the drag. And here you can specify whatever directions you want, which is which, up to you. And also here, important, you need some reference parameters when you do the calculation for a drag coefficient or a lift coefficient. You take the force in Newton and then you scale by what? You use the dynamical pressure, 1/2 rho u squared, and then times an area. And here then you can choose what kind of scales do you want. And I would say it's a good idea just to use 1, 1, 1. And then afterwards you have received the numbers, then you can scale with your own parameters. So your own area, your own velocity, reference, whatever. So I would suggest 1, 1, 1, just to do it easy. But you have to specify these numbers. So here, for instance, if you have an airflow around a wing, and you send in, you have an angle of attack for this wing, some alpha, yes, then you can sort of calculate your own lift and drag directions. Of course, if you don't want to tilt it, yes, you can use the horizontal vertical direction. But then maybe you have to recalculate afterwards if you have an angle of attack. Your choice. Your choice. So also here you can print out some values from your simulation here. Here typically you will print out the minimum and the maximum value. Here for some scalar fields, pressure, the eddy viscosity. So that's actually an option here, operation minimum and maximum. So he will then print them out or save them in a file for you. Could be nice to know while you simulate to see that what is my maximum pressure, what's my minimum pressure right now. You can see that in the printout while he simulates. So then you can crash him if you see this goes totally bananas. Same with the velocity, but that's a vector, so it has a different setup, of course. But it might be a good idea to print these out during simulation. Here also, yeah, you have some options here. He will then even identify which cell do you find the maximum velocity, which cell do you find the minimum velocity or pressure or whatever. That's also an option. And here then, maybe very interesting, how to write out the y plus. Of course, instead of using these functions, you can do it afterwards. When the simulation is done, then you can also calculate the y plus and also get, well, any of these other functions as well, actually. But it could be nice just to include it directly so you have them all the time. It could be a good idea. And here also he will print it out on the screen while simulating. So you just copy and paste these functions directly into your control dict. Field average quantities. Well, they will actually they use this prime to mean function. They will actually try to calculate, say, the turbulent Reynolds stresses, if you like, or whatever. Velocity, pressure, but the fluctuating part. So yes, that's actually also an option. But here, normally, when we're doing two-equation turbulence models, well, we don't have these Reynolds stresses available. So this is more advanced simulation, like full Reynolds stress model or a large eddy simulation, stuff like that. Yeah. And then we have something nice here. We have something probing. This can be very, very useful. Say you want to do a grid convergence index check for your mesh, and then you can here specify locations for what to print out. And I mean, typically when you do a grid convergence index, you have to find good monitors, find good locations that sort of covers the physics inside your problem. But sometimes we have to try several times here. But okay, then you can put in several locations here, and then automatically you will have all these values listed for velocity and pressure at those locations. That can be very, very convenient, especially when you operate with different meshes. Then he will then interpolate it for you for these locations. So that could be very, very nice indeed. And then finally here the vorticity. Yeah, can be nice to have some plot of the different vortexes for the different curves. Could be nice. So, as it says here, if you don't use it in your control dict as a function, okay, then you could use it afterwards. Of course you can. So this is one syntax. So here you write, for example, simple form minus postprocess, and then if you have a dictionary for the setup for whatever thing you want to print out, then you can do it after the simulation is done. So we'll have a look at that one as well. You have some examples here. So here we have a function object something. Why not? And here we have actually done a parallel simulation. So we haven't looked into that one yet, but that's also an option. When you do a parallel simulation, you don't get single result folders. You get one folder for processor number 0, and then another folder for processor number 1, and so on. And inside those folders, you will find your time result folders. But they will just be part of the entire domain. Hence, you have to look into all of them if you want to, say, execute such a function. And if you don't specify either some time limits here, some time folder names, or just the latest time, if you don't specify anything, he will do it on all the result folders that he can find. So your choice. frequently we are only interested in the last one, but never mind. Sometimes you need all of them. Yeah, using sampling, that's another thing. Using sampling, meaning something called a sample dict, and also we have something called probe, and then probe dict. That is also a convenient way to sort of extract data from results in the locations where you want them. So running sample dict or probes dict afterwards, yes, can be easily done like that. Of course, then you have to go through these dictionary files, the setup, what you want. And I think we have some examples here. I think I showed you the generic sample dict file that follows the distribution. I think I had it here somewhere, yeah. It's a very, very big file, so typically you will only pick parts of this one. But here you find a lot of description for the different choices that you have. And believe me, you can choose a lot here. So they have some examples, plot of a line, just some single points, yada, yada, yada. So you can have a look for yourself there. And here, sort of a explanation or a sort of a cute little setup for one single sample dict. So something you have to sort of include here, and then you have some choices which field you should look into. Here, for instance, you have the velocity field. Well, that one we always have. But what about this field, wall shear stress? That's not normally computed. Meaning, if you want to extract data from such a field, you have to create it first. So then you need this function, or you could use also postprocess to create this field first, and then you can afterwards extract the data from it. So here they have some lines alongside starting and ending locations along a line. So then you can get any number of results there. I think here they had chosen the interpolation only to be in your cells up here. So interpolation scheme, cell point. So instead of here specifying I want 100 points or 1,000 points along this line uniformly distributed, then he will only take your cells. So this is also a good idea how you can extract data from the, say, the original location, from the cell centers only, for instance. That's actually possible here. Yeah, it's the same file, a little bit more description. And here then the probe, a probe dict. So specify what fields to sample and where do you want the locations. So if you search your tutorial folders for a probes dict, you will find examples of these. And then in the end you will maybe get something like this. Could be very nice to know. Here also you can specify the coordinates. What do you want? Sometimes it's enough with only the y direction, for instance. Then you only get one number here. But you can specify all three if you want. So you see here, for instance, they are choosing 0, 0 for x and y, and only a change in the z. Then it would be enough actually just to use z values, but your choice. And then scalar give you 1 point, 1 value, and vector gives you 3, of course. yeah, as it says here, you only have one axis coordinate. Do it simple. So this is how such a result file would then actually look in the end. So if you don't then have your functions inside the control dict, you can always do it afterwards. That's also an option, like we did with y plus, and for this example, for the vorticity, for instance. So post-process, that's a good one. If you want to know what can you choose from here, well, you just execute postprocess minus list, and then you will get an idea. Let's have a look. Postprocess minus list. Okay, here you have it. I have in my distribution 64 different options. And most of them I have no idea what they are. Well, Quran number I can understand, Mach number, and so on and so forth. So there you have it. Nice to know. Any questions to that one? Yeah.
I used the sample dict for this task, the exercise 3.
Mm-hmm.
And when I used the plot over line, I always got an average value as well. Is it possible to turn this off when doing a plot over line?
Did you get an average value when you did plot over line?
I got all the raw data, and I also always got the mean value, the average value, something that raw data.
That should be possible to avoid. That should be possible to avoid. Let me have a look at that one. I think I did it. If I now can recall where I did it. I wonder if it was here. No, not there. Nope. Where the heck did I do that one? I think it was here actually. Here we have one. So for instance here, I wanted the velocity profiles at 3 different locations. After 9 meters, 14 meters, and 19 meters, for instance. And I loaded in y and y plus. Here again, I have to create this field before I can execute this, whereas normally he doesn't have y plus, so you have to create that one first. So these two is what I wanted. And then you see what I chose here. I chose midpoint and phase. And also up here, interpolation scheme, cell patch constrained. And if you look at the description inside the generic sample dict, you will find explanation what this means. Midpoint and phase, what does he do? He takes the cell center locations, but he also takes the center for each phase along that line. So for the velocity there is a little bit weird because you will have 2 constant values and they operate in pairs. So it looks a little bit strange. I didn't really need it. But I had to do that one to get my y plus at this x location, because he's only calculated on the cell faces. If you only want the velocity and nothing more, then you could use midpoint and nothing more. Then you will only get the cell center values and that location and nothing more, no average, no nothing. So there you will have a recipe. I was planning on creating a sort of a solution suggestion for exercise 4, so I'll put this one out. Okay? Yeah?
Will we also solution for exercise 3?
The exercise 3, I've forgotten to put that one out for you, yeah. But that was very easy, wasn't it? You don't need a solution. I'll fix it when I get the time. Other questions? Okay. Then I wanted to show you a little setup here. I want to simulate the flow around a plate. So here I have a plate, and then the flow should go around this one quite nicely. That's what I want. I'm not interested in what's happening in front of this plate or over and under, but after this plate I want to see sort of what's going to happen. So I did this one very, very brutal for the plate. I just had one block here, like that. And then over and under, I just created some other blocks, something like that. Then I just specified a solid wall here. But here I have inlet velocities, something like that. And then I used symmetry on top and bottom. Of course, you could put such an object in the middle of your computational domain. That would also be an option, but I just wanted this one to do it as easy as possible. So this is sort of the setup, 3 different blocks, and then I stretched the mesh a little bit, so I had a nice resolution for the center region. So let's have a look at that one. I think I created that one under VKV, if I recall correctly. So here I have the setup. Let's have a look at it. You find this setup actually on the home page. I put it out for you. So let's have a look first at the mesh system, the block mesh. So yeah, I have 3 separate blocks. So I did it easy in the y direction. I have 5 meters for the first block. Then I have 1 meter for the plate, and then 5 meters on top of that one again. And then I went from 0 to 20 meters in the streamwise direction. And I stretched it pretty hard, 0.1 and then 10. But it seems to be working. So no edges, and I have inlet. I had 2 different inlets. Outlet, there I actually had 3, end of each block. And the plate type wall, that's just one, the center block, the left face on the center block. And then the top and bottom was just symmetry planes and front and back. That's it. And let's see now. Let's have a look at the rest of the setup here. I had chosen here a laminar case, and let's start here with a Reynolds number of say 10. My plate is 1 meter, viscosity here is 0.1, and I'm sending in 1 meters per second. And now let's also have a look at the turbulence. Laminar, very easy. And then, just to make sure that we doesn't do anything wrong here, velocity. Yes, I send in 1 meters per second for the inlet, and else rest should be standard. Nothing strange here. And in my control dict, let's see, he should then read simple foam. And I start from 0, and I have maximum 2000, and then nothing strange here, and no functions or nothing. So let's try to run that one and see what happens. First, block mesh, of course. Whoops. Block mesh, thank you. Inlet outlet, plate top bottom. I don't have that many cells, so it's not a big case. And it's a good habit, always run the track mesh. And here, yeah, the mesh is going to be quite beautiful. And then we run it, should be quite fast. Simple foam, and done. He used 100 iterations. Solving for the velocity and the pressure, and the residuals are cute and small and very beautiful. So let's have a look. Here we go. So there we have our mesh system. As you can see, stretched pretty hard towards the center, a little bit too hard actually. So the cells over up and down here, they look a little bit crazy. I'm not so interested in the solution here anyway. I mean, these are the symmetry planes, so I really don't care. I want to resolve sort of the center part here. And here, the cells doesn't look so stupid. The aspect ratio may be a little high. Maybe I should have more cells in the X direction here, but never mind. Let's have a look at the solution. Surface, and then we have the velocity. Yeah, that makes sense, doesn't it? So you'll have 0 velocity behind the plate, and then you send in a constant velocity around it. You will have some say, smaller velocities behind the plate, natural. And for the pressure, yeah, we have, say, very low pressure behind this plate, especially up and down, very low pressure indeed. I mean, it's almost a singular point, isn't it? You have a velocity and then a solid wall. So at the corners there, yes, you're going to have very small, very low pressure. So that one should be okay. No questions to that one. Okay. Let's then change the Reynolds number. I will go to 100. Okay. Let's see, I only have one result folder, so let's remove that one. The 100 folder. So now I don't have any results, and I can simulate again. Simple foam. He went all the way to 2000. What's going on? I increased the Reynolds number a factor of 10. Went from 10 to 100. And simple foam refused to sort of give me a converged solution. Very simple problem. Why? No break before I get an answer here. Come on, what's happening here? What's the reason? Yeah.
Problem with tolerance, maybe?
No, nothing to do with the tolerance. I haven't changed anything, so should be the same.
The coarse mesh is leading to high residuals relation.
No, the coarse mesh is actually not a problem. I mean, look at the residuals. No problem. Trick question. Think of the physics in this problem. I think I have it here somewhere. Where are we? Where are we? Here we are. Have you seen this figure before? This is flow around a cylinder. And for very, very low Reynolds number, you have what we call a creeping flow. So you sort of have a symmetric velocity field in front of and the back. But when you sort of start to increase the Reynolds number, Well, it's going to be a little bit more asymmetric, but you will have a stable solution for this one behind the cylinder. But if you go into this range, what's going to happen? Then you get this alternating vortex shedding up and down. The flow becomes transient. This is nothing I have asked for. This is hidden inside Mother Nature. But the simple foam, he's a steady state solver. He doesn't have the time derivative term in front of the Navier-Stokes. He's missing a term in the equation now because the flow by nature is now not steady. So we have these nice structures here, and he is not capable of handling it at all. We have, say, the physics has changed since we are in this Reynolds number 100. This was for cylinders, but it will be roughly for the plates. Then if you increase the Reynolds number, then yes, it's going to be transition to turbulence. First, it will still be laminar around the object here, but the wake will become a little bit turbulent, increase even further. Well, here now you have such a high Reynolds number that the turbulence will actually trigger already on the surface. And then even higher Reynolds number, well, then everything is really messed up, to say the very least. Here you will have a quite unstructured flow behind the cylinder, but with even higher Reynolds number, you will actually get this structure pattern again. Here you have to be careful what is turbulence and what is a laminar flow. This one, nice, beautiful vortices that will change in time. This is not turbulence. This is laminar structures. You can see it actually when you go down to Elgseter Bridge and look down into the river. You see the flow behind the pillars. You can actually see these structures. There the Reynolds number is probably all the way up here, fairly high. But the 2D structures here by nature is actually a laminar flow. But here it will then be overlay with turbulence as well. So we have to change our solver. We can't use simple foam. We need a transient solver. Any questions? Then we take a break.